is Ryan Wright, founder and CEO at The Dot.
Thank you very much. It's a pleasure to speak to you today. We've been at this for a long time, and we've got a whole bunch to show you about the research and development that's been underway for new software we call Quine. I want to mention real quick, all the material I'm going to show is available at this URL, so if you'd like to grab it later on, feel free to grab this, and I'll show this again at the end of the talk. But if you've got data in your Kafka, the central problem that we've been trying to answer is, what does that data mean? And so if you're like most software engineers, you plug into your Kafka topic, and then you build custom services that consume that data, do some work on it, and then produce the results to a new Kafka topic. That works great, except those custom services start off really simple, end up turning into this tangled web of complexity as we build a big graph of services that relay messages back and forth. And the state of the art is a mess. So what I want to introduce to you today is new software. It's an open source streaming graph called Quine. Quine is meant to live in between two Kafka topics. It plugs into Kafka on one side, consumes data, builds it into a graph, monitors that graph live on the fly, and then produces those results out to the next Kafka topic. So that big tangle of complexity can be reduced, managed, and scaled inside Quine, plugged into two Kafka topics. So that's what I want to introduce, and it's really using it as a two-step process. So on one hand, you plug it into Kafka and define how you're going to consume your data and build it into a graph. Second is you create what we call standing queries that sit live in the graph. They stay resident. They monitor the graph as it changes, and every time there's a match for your query that you're looking for, new results are packaged together and sent out. So let me show you it live in action. What I have here is a recipe on the left-hand side. A recipe is the configuration that defines the run of Kafka. You can also send the same information through using REST API calls. But for this demo, I'm going to use this empty recipe on the left-hand side. There's a little bit of stuff packed into these, but it's just for cosmetics and for demonstration purposes. The real logic, steps 1 and 2, happens here. Ingest streams and standing queries. So if we're going to create a standing query, here's the minimum possible, ingest stream. Here's the minimum possible ingest stream. Say the type is Kafka. We give it information about our Bootstrap servers. And for this demo, we're going to run this a few times. So let's restart from the beginning of the topic each time. The name of our topic is endpoint. All I have to do to run it is call java-jar and then use this -r for recipe argument. current22.yaml. When I run this, it starts up Quine, uses that configuration as defined in our recipe, starts ingesting data you can see down here. If we go over and look at it in the UI, I can call recent nodes. Here's our data. Read from Kafka. Kafka's running locally on my laptop, loaded with data. And we've got data in a graph, technically. So here's a couple nodes. There's data from the incoming JSON stored on each of these nodes in the graph. But as you can see, it's not very interesting. It's not connected data. So technically, this is a graph, but it's not a very useful one. So let's make it more interesting. I'm going to extend my ingest stream. Whoops. Here we go. I have the option to define a custom Cypher query. Cypher's the graph query language created by Neo4j. As you ingest data, that gets passed as this $that argument into a Cypher query. So I can take my Cypher query and use it to consume a record, pull that apart into multiple nodes in the graph, and start connecting them together. So in this Cypher query, I'm defining 3 nodes built out of one JSON record coming in off of Kafka. And I'm using a function built into Quine called ID_from. The reason Quine can be so fast and so efficient is that it can find nodes in a graph very quickly if we have their ID. ID_from is a built-in function that takes any number of arguments and basically hashes them into consistent ID. So if you give it the same values, you'll get the same ID again. So we can use that to consistently generate IDs for known values in a graph. So as data comes in, we read, in this case, the process ID off of one of our JSON records, and we use it to find the ID of our process node. For the event node, we're using the entire incoming payload, so the entire $that record. And the object coming in is pulled off of the object field here. Once we have the IDs for each node, we can set some properties on them here, and then of course we can create the graph structure that we want. This is creating a pretty simple graph structure. One record turns into this 3-node pattern. A process has an event edge that points at the event node, and that has an event edge that points to the object. Let's run this one and see if it looks any nicer. Same command, I'm just running my recipe again. Starts up, data's ingesting. Let's reload and call recent nodes. Here we go. So we've got a process here that read something file-like. Our data here is from a cybersecurity example, trying to find advanced persistent threats inside of a computer. So I'm watching what processes are doing. Here's a 3-node pattern built out of that ingest query we just looked at. Great, so we're well on our way. Let's go ahead and add a second ingest query. This works essentially the same way, consumes from a different Kafka topic though. It's reading records from a different topic, building a different graph structure, but they're gonna intersect. And we'll dive into this in a second and see the data, but before we do, I wanna show you the next feature, standing queries. When you set a standing query, it lives live in the graph, monitors for as complex a pattern as you'd like, from a 1-node pattern to a 100-node pattern, anything that you'd like. So here I'm gonna define a standing query, the first part of it at least, by saying, watch for this pattern. In this case, my example data is a cybersecurity use case. We want to watch for processes behaving badly, in particular communicating with each other and stealing data, exfiltrating it off the machine. So I'm going to watch for this pattern, which I'll show you visually here in a second. But the first step in defining a standing query is define the pattern that you want to look for. And the second is, what action do you want to trigger? Every time that pattern is found in the graph, what are you going to do with it? In our case, we want to find stolen data. Every time we get a notification that we found that complex pattern in the graph, go ahead and make another query to fetch some extra data, check a few values, and package it up, because what we want to do is send it out to the next Kafka topic down here. So we configure our Bootstrap servers. It's going into the results topic. I'll save my recipe. Let's rerun it again. And down here in the bottom right, I've got a consumer that I can start up for my local Kafka topic that is going to consume from that results topic. And whenever I get a result, it'll echo it out to the console here. So as data ingests, it's consuming from 2 different sources. When that data overlaps, those sources get connected. Even if the data arrives out of order, we don't know how these 2 sources are coming and what order they're producing their data, but as soon as that pattern gets connected in the graph, we get a notification. There's our result in our Kafka topic. So Quine found that pattern in the graph, and it produced a result here to the console. As part of the payload that we packaged up, it includes a URL. I'm going to copy that URL out of the payload. You could be feeding a system that is fully automated or is otherwise driven by humans. So whichever kind of use case you have, if you want to feed it to humans, you can set something like the Quine exploration UI up so that you can come in here, take a look at the data, and in this case, look at, examine, evaluate what you're seeing. This is the pattern that we were monitoring. It's a case where a process like Excel has a write event to a file. That file is later read by another process, then deleted and sent out the network. So it's a case of inter-process communication. So Excel wrote some data to this file. This process over here read it, sent it out the network. We detected this automatically live in real time. If we're notifying a human, you might come in here and want to investigate a little further. What is this nt-clean process? Well, I can right click and say, well, who started it? It was started by the SSH process. That's a remote service. Well, where did it receive data from? Here's the IP address of where it received data. Exactly the same IP address, different port, but same IP of where it sent the data. So here's our smoking gun. We found this in real time by plugging into 2 different Kafka topics. It automatically found this complex pattern and published it out to the next Kafka topic. So to summarize, one of the things I hope you'll take away from this, graphs have a history of being really interesting but too slow to use in streaming data pipelines. That changes now. Graphs are for streaming now. Quine has been tested beyond 1 million events per second, and we're just getting started. It's fast, it's very efficient, it's very cost effective, it can scale to huge data volumes, and it's free and open source. Go to quine.io, you can download it for yourself. It can dramatically simplify data pipelines. And we think it's a real game changer. So if you'd like to try any of this for yourself, you can go to quine.io/current22 and download all the materials that I was showing in this talk. Sample data, you can get the Quine executable, the recipe files there. Try it for yourself. We'd love to hear your feedback. Thanks. If you'd like to talk more, I'll be in the expo booth, probably hanging around the Maraxa booth. So stop by. I'd love to talk more about streaming graphs. Thank you.